Hello again, let me pick back up where I left off and do this example. I kind of had to leave off rather abruptly. So consider the function from the reals to the reals such that f of x equals 3x squared minus 4x plus 5. Last time we got f prime of x equaled 6x minus 4, and we knew we wanted to get a critical point, so we set 6x minus 4 equal to 0, and we came up with x equals 2/3. So we know that whatever min or max we get, it's going to be located at x equals 2/3. Now we know from algebra 2 that in front of our coefficient in front of x squared is positive 3. So from algebra 2, we know that we're going to have a local and, for that matter, an absolute minimum located at x equals 2/3. The x equals 2/3 came from calculus. Actually, you could get it from algebra 2 by doing negative b over 2a. And that would give you 2/3. Like you would get the negative of negative 4 over 2 times 3, the negative b over 2a formula, and that would, from algebra 2, or from algebra, let's just do the first derivative of calculus, and from calculus you take the first derivative, set it equal to 0, and that will also give you 2/3. So, but that's the location of the minimum. It's going to be our local and absolute minimum. So now, guys, to get the actual value of the minimum, you're going to have to take 2/3 and plug it into the original f. This guy right here, the 3x squared minus 4x plus 5. I do that way down here, and I get 11/3. I'll go ahead and spoil the plot for you. I'll do that down here. So 11/3 is our absolute and local minimum. But let's examine things a little further. Let's see what we wrote in between. Note that f prime of x is less than 0 if and only if x is less than 2/3. Again, why do I say that? Because f prime of x, that was kind of terse, wasn't it? I need to put, because 6x minus 4. And 6x minus 4 is less than 0 if and only if x is less than 2/3. You solve that inequality from algebra 2 is what you do. And that's true, that's equivalent to saying x is less than 2/3. They're one and the same thing. That's if and only if. What that means is one and the same thing. And conversely, again, that's kind of terse. F prime of x equals 6x minus 4. And 6x minus 4 greater than 0 is the same thing as saying x is greater than 2/3. These are one and the same. Remember, you add 4 to both sides and then divide by 6, you'd get this. Or you can go from this to this. You'd multiply both sides by 3. And then that would give you 3x is greater than 2. Subtract 2 over, that would give you 3x minus 2 is greater than 0. Multiply everything by 2, that would give you 6x minus 4 is greater than 0. See, they're the same, they're equivalent. You can do algebraic tricks to go from here to here, or to go from here to here. These are if and only if means equivalent. Okay, hence f of x is greater than 0 to the immediate right. So what have we shown? Now, guys, remember, greater than means to the right of, so to the immediate right of 2/3, and we could just as well say, since it's to the right, we can say to the immediate right. So to the immediate right of 2/3, f prime is positive, so we're increasing. To the immediate left of 2/3, f prime is negative, so we're decreasing. Okay, and that's by the previous rules that we laid down. And you're like, well, Jason, why do you say? How can you say that? Why are you justified in saying that? It's by our previous rules. If f prime is positive, we're increasing. If f prime is negative, we're decreasing. That's by the rules that we had way up here a long time ago. I forgot when I told you about. We did that a video or two ago or something. I don't remember. It's not been that long ago that I went over that with you. Yeah, right here. We did that right here. It's by these rules up here. Okay, but anyway, but in any event, in a way, going back up is probably more distracting than it is helpful. But I wanted to show you why that I didn't just pull that out of thin air. But anyway, where were we? So since f prime is negative, for x to the immediate left of 2/3, really for x to the left, anywhere to the left of 2/3, f prime is negative. But to the immediate left is what we really care about. So to the immediate left of 2/3, f prime is negative. F prime is negative, so we're decreasing to the immediate left of 2/3. And in a similar fashion, we're increasing to the immediate right of 2/3. F prime is positive, so we're increasing. And by the previous rules that we laid down, we have a local minimum. And you know what? I'm wrong. Wait, we laid that down just up here. Sorry, I went to the wrong set of rules. My bad. That was just, where did I lay that? Oh, I'm sorry. That was just right here. My bad. Oops. That was from the rules I just laid down just a few minutes ago. Sorry, guys. That was just these rules up here. That's just these right here. My bad. That was just the last video. Okay. That's just these rules right here. Okay. So that'd be, and in particular, it'd be this rule right here. So again, f prime negative to the immediate left and positive to the immediate right means a local minimum. And we just get lucky because our example is so nice and so wonderful. It happens to also be an absolute minimum. But now to be an absolute minimum, you have to go in and check. It has to be really nice for it to be local and absolute, you know. But we get the best of both worlds here. Now local is, the rules above just give us local, you know. This one happens to be both local and absolute. But anyway, there's that. And now what is the minimum? X equals 2/3. That's the domain value that we're located at. What's the y value? What is the minimum value, aka the y value of the minimum? You have to plug 2/3 into f right here. F of 2/3 is all this stuff right here. Plugging 2/3 into this guy, and you get that 11/3. Okay. So moving on. So that was the first derivative test. How you're behaving to the immediate left and immediate right. Now the second derivative test, let A less than B less than C less than B, and let F be twice differentiable on the entire open interval. If F prime of C is 0 and F double prime of C is greater than 0, then F has a local minimum at x equals C. For an example, consider f of x equals the cosine of x located at x, and consider the point x equals pi. Consider again f of x equals cosine of pi at x. Consider f of x equals cosine of x at x equals pi. Excuse me, I got tongue tied there. At x equals pi, we have a local minimum. That minimum value is -1 because the cosine of pi is -1, and it occurs at x equals pi. The actual value is cosine pi equals -1, you know. To the immediate left, let's see, for the cosine, to the immediate left, f prime for the cosine, how do we behave? To the immediate left, we have, according to our rules, to the immediate left, our slope would be positive. By the first derivative test, to the immediate left, our slope would be positive, and to the immediate right, our slope would be negative. But the second derivative test is actually friendlier here. Guys, if I did f double prime of x, I would get the negative cosine of x. Which would be the negative cosine of pi, which would be -1, which would be +1. I would get +1, and that it would be +1 is naturally greater than 0. Oh, okay. Let me finish what I started here. I need to finish what I started. So let me do that. Let me finish what I started. I would get f double prime equals neg cosine, and in particular, I want to do f double prime at a particular point, not just any OX value. At pi, since that's what we're talking about, you know. Come on, be nice. It's, I can't type. Let me see. I can't seem to type anymore. So that would be the negative cosine of pi, because remember, the second derivative of the cosine is just the negative cosine. And then now that would technically be -1, but that's +1. and I. That's greater than 0. Okay. Oh, but, well, now there is something else we got to check. We got to check that the first derivative is 0. The second derivative is positive, but it's no good until we check the first derivative at that same point. We got to check the first derivative at pi as well. At the same time, we got to check these simultaneously. And f prime of pi. Now, the first derivative of the cosine is the negative sign. And then, but hey guys, the sine of pi is 0, and negative 0 is just 0. But that's what we want. Okay, and by the second derivative test, I need to separate this because this is an example. I need to separate the example from the abstract. This right here is the actual rule, and this right here is an example following from that rule. So let me put example. There we go. Here's the actual rule, and here's an example illustrating that rule. Okay. So there it is. So I picked the cosine function, and I picked pi as a point for a minimum, because cosine of pi is negative 1, and because I knew, and indeed that is true, the second derivative test betrays the fact that f prime of pi is negative sine pi, which is 0. F double prime of pi is negative cosine pi, which is positive 1, which is greater than 0. And that I get what I want. These two things come true. What happens, guys, if these two things come true, the second derivative test promises me that f has a local minimum at pi. We already know from common sense and trigonometry that that's the case, but the second derivative test tells us that if we didn't even know any better, that would be true. Even if the function was much less obvious, the second derivative test would promise me that this would be true. Okay? Let's go down here. Let a less than c less than b, and let, again, f be twice differentiable on ab. If f prime of c is 0 again, now this time if f double prime of c is less than 0 this time, then you might could guess f has a local maximum at x equals c. And consider f of x equals the sine x at x equals pi halves. And again, we could finish what we started. We get f prime of x. Now that would just be the ordinary cosine. Or let's not do f prime of x. Let's do the actual point that we're interested in. That would be pi halves. F prime of pi halves would be the cosine of pi halves, which is the first derivative. We want that to vanish, and it does. The cosine of pi halves is 0. And now if we do the second derivative, it better be negative this time. So the first thing that we wanted to come true came true. Now f double prime of pi halves, do we get fortunate again? Now if we derivate the cosine, we get the negative sine. Now the negative sine of pi halves, that's going to be not positive, but negative 1. And that's negative 1. And that is, of course, less than 0, commonsensically. And we get what we want. And hence the second derivative test promises, and we are good to go. The second derivative test promises us that pi halves is a local maximum. But anyway, there's that. As it turns out, guys, the trig functions, if you take the domain of all real numbers, you have an infinitude of local min and local max. So that's kind of interesting. Okay, but anyway, let's go down here. Let a be less than c less than b, and let f be twice differentiable on ab. If f prime of c is 0, and if f double prime of c is 0 as well, then f has a saddle point at x equals c. This is neither a local min nor a local max. A prime example of this is our old buddy f of x equals x cubed. Remember, for y equals x cubed at the origin, the origin is neither a local min nor a local max. We are flat there. It's true that we're flat. It's true that the first derivative vanishes there, It's actually true the second derivative vanishes there too, though. And that's the problem. The second derivative vanishes there. It's a saddle point. It looks like a good place to sit down. It looks like an old man is sitting down there, so to speak. It's neither a local min nor a local max, even though we're flat there. It's called a saddle point. And then, again, here's that same old example. The 3x squared minus 4x plus 5 example. Again, you get f prime of x equals 6x minus 4. We did this before. And our only, x equals 2/3 is our only minimum. You know, I'm not going to go through this again because we did this before. So let's not do that again. I don't know why I put that there again, to be honest with you. No harm. I'm going to leave it. No harm, no foul. Let a be less than b, then we say a function is strictly increasing. I did this before, and strictly decreasing, I've already done that. I defined that up there. And we already know our old buddy the parabola is strictly increasing on the open interval 0 to infinity. Okay, and it's strictly decreasing. Again, f prime of x is, we know since that f prime is purely positive for x on the positives, so hence we know that f itself is strictly increasing. The original function f itself is strictly increasing, and we know now f prime is negative on for x on the negatives, so we know f itself is strictly decreasing on the negatives, coming from the left to right. And guys, remember, for increase and decrease, we always go left to right, no matter what. And remember, when I talk about smile and frown, I'm always talking about the graph of f itself, not f prime or f double prime. I'm always talking about the graph of f itself. Now, when I'm talking about the change of signs, you know, that's when I was talking about f double prime. It was kind of clear from the context, but I should have maybe clarified that a little better. It was clear from my examples and from the context. I don't really have to go back and recapitulate or anything. But it's when I say concave up and concave down, it's f itself that I'm talking about. And when I say smile and frown, it's f itself that I'm talking about, or the graph of f itself, I should say. The smiling and frowning, that's the graph of f itself. Concave up and concave down, that's the graph of f itself. Now, when it comes to concave up and concave down, when it comes to negative and positive, that's f double prime, okay? Just to reiterate and to review, okay? That's f double prime that's negative and positive. Negative for concave down, f double prime is negative for concave down, f double prime is positive for concave up, okay? Now, increase and decrease, remember, let's just review f prime is positive for increase, and f prime is negative for decrease. And it's 0 for constant. Okay, but anyway, there's that. And that's just a review. This stuff here was just review, okay? And I'm not going to go through this stuff. You can ignore this last slide here. Let's just ignore it. And that's a wrap for that, guys. I just wanted to review. And remember, it's the graph of f that smiles and frowns. And when we say concave up and concave down, it's the graph of f. We're not talking about the graph of f prime or the graph of f double prime for that matter. Okay. And indeed, it makes sense from the context of examples like x cubed was smiling and frowning. It wasn't, you know, if we did f double prime of x cubed, that would be 6x. And 6x doesn't smile or frown. That wouldn't even make sense anyway, you know. But anyway, moving on. Thank you. I hope this helps. I'll see you on the next video. Bye-bye.